Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element curium. What you see here is a pretty poor photograph of a very small sample of actual curium metal. What's spectacular is that the alpha radiation given off by this tiny sample ionizes the air surrounding it, causing it to glow magenta. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Curium is the 96th element in the periodic table. Its atomic number is 96 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Dmitri Mendeleev, often considered one of the fathers of the modern periodic table, was trying to make sense of how the elements related to each other. He was smart enough to know that he didn't know everything, and there was room for future discoveries. His table was originally published in 1869, and you can see he future-proofed his table by leaving spaces for as yet undiscovered elements. In our case, he left a space for curium after the also as yet undiscovered neptunium, plutonium, and americium. Like all the elements in this part of the periodic table, we don't have to go back in history very far for the discovery of curium, only back to the Manhattan Project during World War II. Curium was co-discovered by this group, Albert Ghiorso, Ralph James, and Glenn Seaborg. Seaborg received a Nobel Prize for his work discovering or co-discovering new elements, 10 of them, and element 106 is named after him, Seaborgium. Albert Ghiorso was involved in the discovery of 12 elements, more than anyone else, though he, unfairly in my opinion, never received a Nobel or had an element named after him. When the existence of curium was declassified in 1945 after World War II, Seaborg announced the discovery of the element in an unusual forum. Rather than at a stuffy scientific conference or in a prestigious academic journal, he made an appearance as a guest scientist on a radio show called Quiz Kids. I was able to find the actual audio of that announcement. Let's listen. I've slightly edited it for length.
Thank you, Bob Murphy, and good evening, everyone. Well, children, we have the great honor to present as our guest observer on this Armistice Day program a most distinguished scientist, Dr. Glenn T. Seaborg. Dr. Seaborg was a co-discoverer of the new element plutonium at the University of California, and he was closely concerned with the development of the atomic bomb at the University of Chicago. And now I have the honor to introduce Dr. Glenn T. Seaborg.
Thank you, Mr. Kelly. When I was invited to take part in your Armistice Day program, I said I would on one condition, that I was not in competition with the quiz kids.
Richard, how about your question?
Have there been any other new elements discovered, like plutonium and neptunium?
Oh, yes, Dick. Recently, there have been two new elements discovered, elements with atomic number 95 and 96, out at the Metallurgical Laboratory here in Chicago. So now you'll have to tell your teachers that to change the 92 elements in your school books to 96 elements.
Yes, you can probably guess where this element got its name. Yes, it was named after the brilliant husband-wife team of Marie and Pierre Curie. Because of the difficulty of separating it from americium, the scientists involved were calling it delirium. Obviously, that name never took hold. Curium is a member of the actinide series of elements down at the bottom of the table. It's the 8th element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides and their isotopes are radioactive. Let's look at isotopes. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 96 protons for curium. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 19 known isotopes of curium, and as I mentioned in the previous slide, we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of curium are radioactive. We don't really find curium in nature. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place. You've used a topographic map to find your place, I assume? All these various isotopes of curium occupy the same place in the periodic table. Of the isotopes of curium, these are the longest lived, the ones with half-lives over 1 hour. Curiously, there are a lot of these. More on half-life in the next slide. The longest curium half-life is curium-247, with a half-life of only 15.6 million years. Now, that may seem long, but is actually very short compared to the 4.5 billion year age of the Earth. Actually, the Earth is 288 half-lives older. That's why it's not found in nature. All the curium has decayed away. It has to be manufactured. More on that later. All radioactive elements decay and transmute into other daughter elements, something the ancient alchemists dreamed about but didn't know was happening around them all the time. Although I'm simplifying this a bit, atoms can decay by alpha or beta decay. I want to show you the decay series of curium. First, let's look at what alpha and beta decay look like on this chart. We're only using a very small portion of a much larger chart. On this chart, the horizontal axis shows how many protons plus neutrons are in the nucleus. This is related to the atomic weight of the isotope. The vertical axis is the number of protons in the nucleus, its atomic number. Since the atomic number also tells us what element we're dealing with, each row is one unique element. As I mentioned, when an isotope decays, it can do this by emitting an alpha particle or a beta particle. An alpha particle is made up of 2 protons and 2 neutrons, 4 particles in total. So if we start with something like radium-226, it has 88 protons. All radium isotopes have 88 protons. Radium-226 decays by alpha emission, meaning it loses 2 protons and 2 neutrons, 4 particles in total. This means we need to move 2 rows down for the 2 protons and 4 rows to the left for the 4 total particles. You can see we arrive at radon-222. Okay, this is the move for alpha decays. What about betas? Here, one of the neutrons in the nucleus becomes a proton and an electron, still electrically neutral, and the electron is spit out of the nucleus as a beta particle. This means the nucleus gains a proton but does not change its atomic weight significantly since electrons are so light. This time, we'll start with thorium-234. Gaining a proton but not changing atomic weight moves us up 1 row, and we now have a new element, protactinium, but with the same weight, 234. This is what beta decay looks like on our chart. Now let's get to the curium decay series. As curium decays, we'll see it transmutes into other elements. After a few decays, which I'll detail, we'll arrive at uranium-235 and a decay chain we've seen before called the actinium series. We'll start with curium-247, the longest-lived isotope. For the first few decays, I'll put the isotope, decay mode, alpha or beta, and half-life at the top of the screen. Curium-237 decays by alpha to plutonium-243. This decays by beta, remember we move up one row for beta, into americium-243, which decays by alpha to neptunium-239, and then by beta to plutonium-239. Plutonium-239 decays by alpha to uranium-235. At this point, we've already seen the rest of the decay series, so I won't bother you with the details. Through a series of transmutation, the uranium-235 eventually decays to lead-207, which is stable and not radioactive. If you want all the details of the actinium decay series, check out the Tales from the Periodic Table episode on uranium here. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any radioactive isotope. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait one half-life, 1/2 of your isotope will decay, and we'll have 512 atoms left. If we wait one more half-life, half of that half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice that there's one remaining atom after 10 half-lives? If we waited one more half-life, our remaining atom would have a 50-50 chance of decaying in that time. Since we're on our 13th radioactive element, 14th if you include bismuth, I'd like to repeat how radioactivity is measured. There are 3 interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity, the rate particles are emitted. This is probably the simplest thing to measure. You can use a simple Geiger counter and just count the number of detections per second. But you need to take into account the size or area of the detector and its distance from the source and multiply the measured counts per second as if your detector could completely surround the source to catch all the disintegrations in every direction. The international unit for this is the becquerel, named after Henri Becquerel, who discovered radioactivity. 1 becquerel equals 1 disintegration per second, so most sources are in the kilo, mega, or even gigabecquerel range. In the U.S., we also use an older unit, the Curie, obviously named after our dynamic duo Marie and Pierre Curie. 1 Curie is the amount of radiation given off by 1 gram of radium. Radium was discovered by them. Get it? 1 Curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Compared to the 1 Curie per gram for radium, Curium-247, with its longer half-life, emits 0.17 Curies per gram, about 1/6 as much. Radiation carries energy, and that energy is deposited in your body or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is about the amount of energy used to lift an apple from the floor to a table. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A Gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milli or micrograys or something like that. In the U.S., we have used a unit of the rad, or radiation absorbed dose, which is 1/100th as large as the Gray, but still a large amount of radiation. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation, alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to the specific kind of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the U.S., we also use the rem, which stands for Radiation Equivalent Man. The sievert is just 100 rem, and the rem is 1/100th of a sievert. These are human health-based units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer, genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts, or 5 rem, per year in the workplace. You normally absorb about 67 millirem every year from the environment around you. That's 1/75th the allowed annual dose. A dental X-ray exposes you to about half of a millirem. A standard chest X-ray, front and side, exposes you to up to 10 millirem, and a chest CT scan gives you up to an 800 millirem dose. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits always outweigh the risk. I normally talk about the abundances of elements on this slide, but because of the relatively short-lived radioactive nature of curium, at least compared to the age of the universe, there's not much to say here. There's really none to speak of in the universe, having all decayed away by now, and none in the sun. Likewise, none in meteorites, or in the crust of the Earth. It's absent in the oceans, and of course, thankfully, none in us. That was a lot of red X's. So, how did these guys go about creating and discovering a new element? They used the new 60-inch cyclotron built by Ernest Lawrence at the UC Berkeley Radiation Lab, later called the Lawrence Radiation Lab, and even later the Lawrence Berkeley National Lab after the word radiation became too politically sensitive for Berkeley. In the accelerator, they started with plutonium-239. This was available from production for the Manhattan Project. The accelerator is used to produce a stream of alpha particles. Remember, an alpha particle is a naked helium nucleus consisting of 2 protons and 2 neutrons. When these alphas hit the plutonium-239, you get curium-242 and an extra neutron. Making curium like this with a cyclotron is a slow, expensive, and not very productive method. Most curium is derived from nuclear reactors, where you also have plutonium byproducts of the uranium fission process and lots of neutrons to spare. You only need to separate and purify spent nuclear fuel, and you can get as much as 20 grams of curium for every metric ton of spent fuel. How does the curium come to exist in the spent fuel? Let's take a look at that process. It's a bit more complicated than shooting alpha particles at plutonium. In fact, it's a multi-step process, but not hard to understand. Again, we're going to start with plutonium-239, normally found in uranium-based reactors as a byproduct of producing power. Plutonium-239 has a half-life of just over 24,000 years, so we don't have to worry about it decaying away during this process. Remember, in a reactor, there are lots of free neutrons available from the fission process. Eventually, our plutonium-239 will be struck by a neutron and changed to plutonium-240. Again, plutonium-240 has a long enough half-life, 6,561 years, that it will hang around for a while too. That nucleus can also be struck by a free neutron and transformed into yet another isotope of plutonium, plutonium-241, with a fairly short half-life of only 14.33 years. This shorter half-life is good because the next step depends on its decay by beta particle emission to americium-241 with a half-life of 432.6 years. This new element absorbs yet another neutron and becomes americium-242. Americium-242 has a nice short half-life of 16 hours, which is also good news since we need it to decay by beta particle to our target Curium-242. Notice the relatively short half-life of this Curium isotope, only 162 days. Separating and purifying this Curium must be done quickly, or you'll have none left. Given its rarity, if you had a reason to buy Curium, you'd need to buy it through the National Isotope Development Center. They support the Department of Energy in coordinating the production and distribution of a variety of isotopes used in industry, research, and medicine, including the isotopes of Curium. They were extremely kind and provided information aiding in the production of this episode of Tales from the Periodic Table. My thanks to them for their help. Curium isn't the most costly element, but it ain't cheap either. All I could find online was a price of $185 million per kilogram. I'd expect a high price given the process we saw a couple slides ago, in addition to separation and refining it from spent nuclear fuel, so I'm dubious of my figure here. If anyone knows better, please leave more accurate values in the comments. Unfortunately, the NIDC from the previous slide is not allowed to reveal pricing except to licensed organizations capable of handling these types of dangerous materials. Quite understandable, and I'm not one of those licensed organizations. We can talk a bit about a few physical properties of Curium, but not a lot is really known about this rare element. As you can see, most of the properties have an N/A, not available, next to them. Still, there are a few things we do know about Curium. Curium has a density of 13.51 grams per cubic centimeter. It's a fairly dense element. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds for comparison. You can see curium's density is even higher than lead at 11.34 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, Curium's density is 13.51 grams per cubic centimeter, near the top of the chart, the 15th densest element, very near the density of mercury. Curium has a melting temperature of only 1,345 degrees Celsius or 2,453 degrees Fahrenheit. That's the 40th highest melting point, about the middle of our chart and only slightly less than silicon or nickel. Curium boils at 3,110 degrees Celsius or 5,630 degrees Fahrenheit, giving it the 31st highest boiling point of all the elements, above average on this chart. That's 1,765 degrees Celsius above its melting point, giving it a smaller liquid temperature range than most of our recent elements, such as neptunium, uranium, and plutonium. Please refer to their videos. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range. As I mentioned, curium's liquid temperature range is a little higher than average, with a 1,765 degrees Celsius range, the 35th largest liquid temperature range of the elements. The smallest liquid temperature range belongs to neon, which is liquid in only a 2.51 degrees Celsius range. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. If we compare the size of the curium atom to that of hydrogen, we'd see something like this, though I'm just estimating the atomic diameter by using its covalent diameter, the only figure I could find. The curium atom is slightly less than 4 times the size of hydrogen. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are disquietingly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium on the bottom right. My estimated size of the curium atom places it in the upper region of the chart, around the size of many of the rare earth lanthanides. It's about the same size as tantalum, between zirconium and calcium. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of curium. It has a moderately simple spectrum with a smallish selection of colors. Interesting to note here is the complete lack of any greenish colors. This means these colors of light, when combined, would probably look magenta, since white light minus green is magenta. See my video about color mixing for more on that subject. Spectra of the elements uniquely identifies them to scientists, as each element gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Okay, I know, you're thinking, we're getting pretty high up in the periodic table. There can't be that many applications for curium. And you'd be right. But there are a couple. Before I continue, the tiny lump you see on the right purports to be a very small piece of actual curium metal. Like many of its radioactive predecessors in the actinide series, curium is a strong emitter of alpha particles. This is useful for a few applications. Remember, an alpha particle is just a helium nucleus consisting of 2 protons and 2 neutrons. Curium alpha sources are part of many instruments on spacecraft sent to other bodies of the solar system, in particular Mars. These sources are part of an instrument called an alpha particle X-ray spectrometer, or APXS. On the right is the instrument itself, isolated from the spacecraft, and on the left you can see it as one of many instruments on the arm of the Curiosity rover on Mars. The alpha particle X-ray spectrometer was present on many of our Martian surface fleet of rovers. First used on the microwave oven-sized Sojourner rover as part of the Pathfinder mission, then on the Mars exploration rovers Spirit and Opportunity, then on the Curiosity rover as previously mentioned. Here's a view of Mars from Pathfinder's Carl Sagan Memorial Station. You can see the Sojourner rover nuzzled up next to a rock named Yogi as it used its alpha particle X-ray spectrometer to analyze its composition. And yes, there were many other fictional names given to features visible to Pathfinder. Pooh Bear, Stimpy, Casper, Scooby-Doo, Roadrunner Flats, Indiana Jones, and Zaphod, to name a few. Well, there's a lot of rocks to name. The Philae lander was part of the Rosetta mission sent to Comet 67P Churyumov-Gerasimenko. Philae and its accompanying APXS attempted a landing on the comet's nucleus, which was partially successful. So, how does the APXS work? Alpha particles streaming from the Curium source strike atoms in the sample. By the way, the sample you see here is a slice of Martian meteorite. Some alphas rebound from the nuclei of the target sample. The rebound energies give a clue about the masses of the target atoms. This method is more sensitive to lighter target nuclei. At the same time, the alpha particles excite X-ray emissions that also give clues to the composition of the target. The X-rays are more sensitive for heavier nuclei. Heat can be generated by radioactive decay. This is a pellet of plutonium-238, not curium. The pellet is red hot because it's so radioactive the alpha particle emission heats it to this temperature. This heat can be used to generate electricity in what's called a radioisotope thermoelectric generator, or RTG. NASA's version of this is called the Multi-Mission Radioisotope Thermoelectric Generator, or MMRTG. Curium-244 has been proposed as a substitute isotope instead of plutonium-238. It has a half-life only 1/5 of plutonium-238, so it won't last for long missions, but it generates about 5 times the energy per gram, about 3 watts per gram, so you won't need as much of the isotope. Though both emit alpha particles when they decay, curium also emits more neutrons and gammas, which may make it impractical for this application, since it would require more heavy shielding. Currently, plutonium is heavily used in deep space and planetary missions by NASA. The New Horizons spacecraft, which recently visited the planet Pluto, had one of these nuclear generators on board. You can't use solar panels that far out. The Sun, almost 4 billion miles distant, looks like a very bright star in Pluto's sky. There's not enough light energy to generate the needed electricity. New Horizons MMRTG supplied about 245 watts of power at launch. As the spacecraft continues on its mission, the plutonium decays, supplying exponentially less and less power, until, in the late 2030s, the generated electricity won't be enough to power or heat the spacecraft. MMRTGs were also used in the Pioneer and Voyager spacecraft, which have now left the solar system and are sailing through interstellar space. Curium serves no known biological purpose, and you, hopefully, have none of this stuff inside you, though there were some early attempts to use curium to power long-lived pacemakers. Fortunately, technology in the form of better batteries and more efficient electronics has rendered the nuclear pacemaker obsolete. I couldn't find a photo of a Curium-powered version. This one used plutonium-238. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about Curium. Crew member assigned to spectrometer duty on the Mars rovers. In the next program in this series, I'll examine the element berkelium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element curium. For more Tales from the Periodic Table, see this playlist on my YouTube channel. And of course, I'm required by law to say this, smash that subscribe button.